All right, so let's start. Today you are going to learn chapter 19, which is about DC circuit. Okay. All right, so first let's start with electromotive force. Okay, in short, we call it EMF. So EMF means electromotive force. And by the way, electromotive force is not a force. Okay, it's a potential difference between two terminals of a battery or a generator when the battery or the generator is not connected to an external circuit. Okay, so yeah, make sure you don't confuse the electromotive force with force. Okay, so electromotive force is basically a potential difference. Okay, when it is not connected, when a battery is not connected to a circuit, to an external circuit. Okay, now the question is why the potential difference between two terminals of a battery is different when it is connected, when it is not connected to an external circuit. Okay, so to understand this, let's consider this battery. Okay, I think the simulation probably helpful. Okay, so let me go to the simulation and then come back here. Okay, so here you see that we have a battery here, and then this device at the bottom can measure the potential difference or the voltage between the two terminal of a battery. Okay, so currently it is 9 volt. Okay, and now if I connect it, okay, so you will see that it is basically a 9 volt, and that because okay, so you see that it's still 9 volt. Okay, and that because it is a simulation. Okay, in simulation we have the control to change the parameter. Okay, now in all real battery, there is something internal. Okay, we call it internal resistance. Okay, because of that internal resistance, when the battery is connected to an external circuit, so here you see this battery is connected to a resistor at the top. Okay, so when a battery is connected to an external circuit, because of the internal resistance, the potential difference between the two terminals of a battery is not the same. Okay, now it is same because here there is no internal resistance, but we can change it. For example, here at the right hand side, there is something called battery resistance. So we can change the battery resistance. Let me change it to some value. Okay, now you see that the battery voltage is 7.5 volt. Okay, and if I disconnect it, okay, so let me disconnect. So if I disconnect it, you will see that again it is 9 volt. Okay, so now because here we consider the battery's internal resistance. Okay, when the battery is not connected to the to the external circuit, it's still showing 9 volt. But when it is connected to the external circuit, you see that it becomes 7.5 volt. Okay, all right. So now let's go back to here. So you see that this is the internal resistance. So if I draw a schematic diagram of a battery, instead of just this one, okay, for a real battery, we have this component also, an internal resistance. And for internal resistance, we use this symbol, small r. Remember that normally for resistance, we use capital R. For internal resistance, we use small r. Okay, for most of the problem, I mean, for most of the concept and the problem, we are going to neglect the internal resistance. Okay, um, I mean, because it is very small. Okay, but for a few numerical problem, we consider these. Okay, to understand the concept. Okay, so that's what we need to understand. But for most of the problem, we are going to neglect it. Okay, now so if we look at this diagram, okay, then we so here for electromotive force we normally use this symbol, curly E. Okay, so instead of writing V, okay, we use curly E. Okay, so curly E means the electromotive force. Okay, and this is the E when it is not, this is the potential difference when it is not connected to any external circuit. Okay, now what is the relationship between E and R and the potential difference between this point and this point? If the potential difference between this point and this point is VAB, so the relationship between VAB, curly E and R is this. Okay, so VAB, the potential difference between the two terminals of a battery, is equal to E, so this curly E minus IR. Okay, so you know that the IR is basically voltage drop in R. Okay, so you know the voltage drop from the Ohm's law, voltage is equal to I times R. That's why you see that. Okay, now if it is not connected to the, if the battery is not connected to any circuit, then you know there will be no current. Okay, so no current means this term is equal to 0, and that time the terminal voltage, terminal voltage means the uh, voltage or the potential difference between two terminal is equal to the EMF. Okay, but when it is connected to to some external circuit, then you will have this term. Okay, when it is not connected to a circuit, then this, the potential between two, potential difference between two terminal is exactly equal to the electromotive force. Okay, all right. The next thing is the resistance in series and resistance in parallel. Okay, now the resistance, several resistance can be connected this way. So you see here R1, R2, and R3 connected something like this way, one after another. Okay, and another possibility is this. Okay, on top of another. Okay, okay, so this combination is called parallel combination. You see they are parallel, and here this combination is called the series combination. Okay, so series combination of the resistance, and this is the parallel combination of the resistance. Okay, now I want to know what is the total resistance. So if I want to know what is this combination, okay, in altogether we call it equivalent resistance. So I want to know what is the equivalent resistance when R1, R2, and R3 connected in series or connected in parallel. Okay, all right. So to understand, to derive that part, that equation, okay, let's label all the components. So this is R1. Okay, this is R1, this is R2, this is R3, and this is the potential difference. So V and E is basically the same thing. Okay, in some circuit you probably see this curly E, and in some circuit it is V, as I mentioned already. Normally we neglect the internal resistance, then this V is equal to E. Okay, all right, so in some circuit if you see E, don't be surprised. Okay, now as you know that the direction of the current is this. Okay, so you see that the same current basically goes through all the resistances. Okay, it's basically very similar to this analogy. Okay, so here let's say we have 3 toll. Okay, so you see that all the car should pass all the toll booths. Okay, because there is only one way. Okay, so similarly you see here for the current there is only one direction to go. Okay, so the equivalent, so the equivalent circuit of this circuit is this one. So here V is the same V, but because we want to know what is the combination of these three resistances, so I write Req okay, which means the combination of all these resistances. Okay, and if you compare this with this one, you see that the same current I is basically flows through Req. Okay, now in this circuit here, in the right circuit, I can write V equal to IR, right? IRQ, right? And here it is different. In the left hand circuit, it is little bit different. Now you know that here in R1 the potential drop will be IR1, the potential drop here will be IR2, and the potential drop here will be IR3. Okay, so you see that the voltage drop or the potential drop in each resistances are different. So let me call it V1, V2, and V3. Okay, and if there is no loss, okay, in any other component, and so there is internal resistance, but we are neglecting here the internal resistance, and normally the resistance of the wire are also very small, so there is no other component where the potential can be dropped. So we can write the battery voltage is equal to V1 plus V2 plus V3. Okay, now V, the left hand V is equal to IRQ. Okay, because this same V is equal, I mean, the V and this V are the same. So I can write IRQ, and V1, we can write IR1, V2, I can write IR2, and V3 is IR3. Okay, so it tells us that when the resistances are in series, connected in series, then the equivalent resistance is basically the sum of all the resistances. Okay, so this is for the series resistances. Okay, how about the parallel resistance? Okay, so here you see that now the current has three ways to go. So when the current is here, it can either go this way or this way or this way. So current breaks in three different components: I1, I2, and I3. Okay, so you can write just I equal to I1 plus I2, I3. Okay, so I enters here at A and then leaves as I1, I2, and I3. Okay, so I equal to basically I1, I2, and I3. And similarly, I want to know what is the equivalent resistance when the resistors are connected in parallel. Okay, so we can draw a very similar circuit as of the last concept. Okay, so here is basically the same thing, I R EQ. Okay, now here this is the potential drop is I1 R1, here this is I2 R2, and here it is I3 R3. Okay, but here you see that all the line, all R1, R2, and R3, and also V connected here at A and B, these two terminals. Okay, so you see A and B, all the lines are connected between A and B. So it tells us that the potential difference, because the potential VAB is same, okay, and this tells us that VAB is equal to V is equal to I1 R1 is equal to I2 R2 is equal to I3 R3. Okay, so when they're connected in parallel, something like this, and because all the lines are connected between A and B, the potential of all this line will be the same. So here I1 R1 is equal to VAB, I2 R2 is equal to VAB, and so on. Okay, so with this we can derive this equation. Okay, I equal to I1, I2, I3, and then if I solve here this I get V equal to REQ. Okay, so let me substitute this. Okay, and then for I1, okay, as V equal to I1 R1. So if I solve I1, I get V over R1. Okay, so V over R1. Similarly, V over R2, and similarly V over R3. Okay, so if I cancel V from both sides, I get something like this. Okay, so when they are connected in parallel, when the resistors are connected in parallel, the equivalent resistance follow this rule. Okay, and if you compare this with a toll booth, it will be something like this. Okay, so you see that there are different way to go, pass these toll booths. Okay, so similar to the current. Okay, all right. Now, the series resistance and and the parallel resistance are not enough when we have when we have a complicated circuit, something like this. Okay, so here you see that resistances are connected both in series and parallel in one circuit. Okay, for example, you can think that this resistance and this resistance are connected in series, and then there are some other complicated combination which is very difficult to understand if we just want to use the series and parallel combination. Okay, now if we have some circuit something like this, and if you want to solve it, we need to know something called Kirchhoff's rule. Okay, so Kirchhoff has two rules. One is called junction rule, another is called loop rule. Okay, so junction rule we already know. Junction rule tells us that the sum of the currents entering a junction equals to the sum of the currents leaving it. Okay, so we already see it here. Okay, so I enters here, and then I1, I2, I3 leaves A. Here is the junction. So you can write I1, I equal to, so here you wrote I equal to I1, I2, I3. The same thing here, for example, if you think about this junction A again, so here you see I3 is entering A and I1 and I2 leaving A. So in this, for this junction, it will be I3 equal to I1 plus I2. Okay, and here if you think about this junction, so here you see that I1 is entering, here you see I2 is entering, and then you see I3 is leaving. So here it will be again I1 plus I2 equal to I3. Okay, all right. So this is the junction rule, which is easy to understand. Okay, you can compare it with this water pipe analogy. Okay, so here you see that water is entering from this side and leaving from this side. Okay, so the flow rate of this one plus this one will be equal to this one. Okay, all right. So the next one is the loop rule. And the loop rule tells us that the sum of the change in potential, okay, or the potential drop around a closed loop is equal to 0. Okay, so for example, what is the closed loop means? So closed loop means this one. Okay, so for example, if I want to talk about this circuit, so this is a closed loop, this is a closed loop. So here we have two loops, and we can make another loop also. For example, if we neglect the middle one, okay, then this will be another loop. Okay, all right. So here we have three loops. One is this one, another is this one, another is the whole, basically this one. So three loops. Okay, now what is the junction rule tells us? Okay, so for simplicity, we basically consider two loops here. Okay, so this one or this one. Okay, now consider any loop. Okay, so let me consider just the top loop. Okay, so this one. Okay, now here in this loop, voltage drops components are this one. So voltage, so this is a battery. That means there is a change in potential. So there is another resistance. So resistance means there should have some potential drop. Another resistance, there should have potential drop. And also here there should be potential drop. Okay, now if I draw, I mean, if I write the loop rule, I have to choose a direction. So I can either go in this direction or I can go in this direction. Okay, so if you go in one direction, it will be a little bit different than in another direction. The sign will be different. Okay, so I'm going to talk about the sign later. Okay, so let me first write down uh, for this one. If I go this, okay, so if I walk through this loop, okay, then you see, let me start from here. So here you see that I am going from here, from negative to positive terminal of the battery. So it will be 45 volt, and then there is a potential drop at R. Okay, so let me just use the symbol. Okay, so it will be E2. Okay, and then minus I3R. Okay, so potential drop in small r is I3 times R. Okay, so here I put a negative sign. So I'm going to talk about the negative sign. Okay, after I write the equation. And then 40 ohm times I3, because the current through 40 ohm is I3, still I3. Again, I use a negative sign. Okay, and then another potential drop will be at 30 ohm. So, and at 30 ohm, the current is I1. So 30 ohm times I1, and that is equal to 0. Okay. Okay, I1, that is equal to 0. So this is the loop rule. Okay. Now the rule for positive and negative sign are here. I mean, I discuss it here. Okay, so for example, if the direction of walkthrough, so travel, okay, from negative to positive, so if I go in this direction, I mean from negative terminal of the battery to the positive terminal of the battery, then I have to use a positive sign. If I go in the opposite direction from positive to the negative, then I have to use a negative sign in the loop equation. Okay, and that is for the battery or the EMF. Okay, how about the for the resistor? For resistor, it is opposite. If I walk against the direction of the current, then I have to use positive sign. Okay, if I follow the same direction as the current, then I have to use a negative sign. Okay, so you see that for battery and for resistor, they are different. So make sure you understand this. So once you understand this, it's easy to write an equation. Okay, so for example, again, let's consider this one. Okay, so if I follow this red loop, that means if I walk through this red direction, then you see that one of the drop will be here. So that is 12 volt. And you see that the current is, I'm going with the current. So the direction of the current and the direction of my walkthrough is the same. So there will be negative sign for the ohm, I times 400 ohm. Okay, and again for 290 ohm, I will have a negative sign. Okay, and something like this. Okay, so we will be doing some numerical problem, and hopefully it will make the concept more clear. Okay, now how to solve a problem. So when you solve a problem using Kirchhoff law, you have to remember this 4 steps. Okay, so first one is you have to label each current. Okay, identify the unknowns, and then apply junction and loop rules. Okay, and the important thing is you will need as many independent equation as there are unknowns. For example, if there are 3 independent components, then you need 3 equations. If you have 2 unknown, then you need at least 2 equations, and so on. So once you can write the equations, then the next step is to solve those equations algebraically, and make sure you understand the sign. Okay, be careful about the signs when you write down the uh, loop rule. I mean, the equation something like this. Okay, for example, if you go in this direction, okay, the equation will be this. Okay, so the sign is very important. Okay, all right. So far what we learn is how or the what is the equivalent resistance when resistances are connected in series and when they're connected in parallel. Okay, and in Kirchhoff law we see that how to apply the junction rule um, and loop rule. Okay, now the next thing you are going to learn is when the batteries or EMFs are connected in series or in parallel. Okay, so the simplest connection is this one. Okay, so 2 battery connect on top of another. Okay, so here you see that the negative of this battery is connected to the positive. Okay, so if we have some combination something like this, then the total EMF is the sum of, so if it is 1.5, if it is 1.5, so the total EMF will be 3 volt. Okay, so the schematic diagram is this one. So here you see that positive is connected with the negative, and then and then it connected with the other component of the circuit. Okay, normally in flashlight we use this this kind of uh, EMF, and that are in series. Okay, now what about if you connect in opposite direction? For example, something like this. So something like this. So here you see that your positive is connected to positive, negative is connected to negative. Okay, so still they are in series but in the opposite direction. Okay, so if you add 2 battery but in the opposite direction, then if you have 1.5 volt and 1.5 volt, the sum of them will give you 0. So equivalent potential difference will be 0. So it basically does not make any sense, right, if you connect them in opposite direction. Okay, but I mean, for example, if one battery's potential difference is 10 volt and another is 1.5 volt, okay, and if you connect them in opposite direction, I mean, something like this, okay, something like this, then the equivalent EMF will be 8.5 volt, something like that. But you know that again, it is not helping, and you are basically losing energy, right? So normally we don't use this combination, but these combination are used to charge battery. Okay, so for example, in car alternator is one of the EMF source. Okay, this basically charge the battery, right? So if it is the alternator, okay, and if it is the car battery, so you see that here negative is connected to the negative and positive is connected to the positive. So that way you are basically charging this battery. Okay, so here you see the positive is connected to positive and the negative somehow is connecting to the negative. Okay, so when you connect them in the opposite direction, okay, it's basically you are I mean, this is useful when you want to charge a battery. Okay. All right. So this is basically um, the example of the last. So somehow it is here. It's not the EMFs are connected in parallel. So it's not, it should be on the last slide. Okay. So similar to the resistance, you can also connect the EMFs in parallel. Okay. So EMFs in parallel only make sense if the voltage difference or the potential difference are the same. Okay. And this arrangement can produce more current than a single EMF. Okay. Now, yeah, you can see that if there is only one battery, the current would be uh, the current this current would be less than if you have two battery that are connected in parallel. Okay. Okay. All right, so I'm going to stop here. In the next class, I'm going to talk about the capacitor in series, okay, similar to the resistors in series, and then capacitors in parallel. And then how about when a circuit um, include both resistors and capacitors, okay? And I will talk about that in the next lecture.